In this episode, we take a careful look at anomaly detection, which is a set of methods that try to identify unusual data points, unusual behavior, or unusual patterns without always having clear labels for what is bad. This topic matters a lot for beginners because anomaly detection is often described in dramatic terms, as if the model can automatically spot attacks or fraud the moment they happen. In real data work, especially in cloud security and cybersecurity monitoring, anomaly detection is better understood as a way to surface candidates for review, not as a final decision maker. The model usually produces a score that reflects how unusual something looks under its learned view of normal, and your job is to decide how that score will be used. If you overclaim what the method can do, you end up with false confidence, overwhelmed analysts, and blind spots that grow over time. Our focus will be on interpreting scores, choosing thresholds responsibly, and understanding drift so you can keep anomaly detection useful instead of noisy. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Anomaly detection begins with a simple idea that turns out to be complicated in practice. Define normal, then flag what does not fit. The problem is that normal is not a single thing, because real systems have many legitimate modes of behavior. A cloud environment might have different normal patterns for developers, finance staff, automated services, and third-party integrations, and those patterns can overlap in messy ways. An anomaly detection method tries to learn where most data points live in feature space, and then assigns higher anomaly scores to points that live far from the learned bulk. That learning can be explicit, like modeling a distribution, or implicit, like measuring distance to neighbors or reconstruction error in a learned representation. Beginners sometimes assume the model will discover the true meaning of unusual, but unusual is always relative to what the model has seen and how you represent the data. A useful first mindset is that anomaly detection is not a detector of evil. It is a detector of surprise under a chosen definition of normal. The output of many anomaly detection systems is not a label, but an anomaly score, and understanding that score is the first safety skill. A score is usually a ranking signal, meaning higher scores indicate greater unusualness, but the score value itself is not automatically a probability that something is malicious. Two different methods can produce scores on different scales, and even the same method can produce score distributions that shift over time. In security operations, it is tempting to treat a score like a confidence number and tell stakeholders that a high score means high risk, but that is an overclaim unless you have validated that interpretation. A score is more like a smoke signal. It suggests where to look, not what you will find. When you communicate about anomaly scores, the honest claim is that the method prioritizes unusual cases for review under a defined baseline. That honesty protects you from the expectation that every alert is a true incident and keeps the model from being treated as an oracle. Thresholds are how you turn scores into actions, and thresholds are never purely technical because they represent a policy decision about trade-offs. If you set a low threshold, you will catch more unusual cases, but you will also produce more false alarms, which can overwhelm a team and cause alert fatigue. If you set a high threshold, you will reduce noise, but you may miss subtle anomalies, including early signals of compromise. This trade-off is especially sharp in cloud security because environments are dynamic and benign changes can look anomalous, such as a new deployment pipeline, an emergency access event, or a temporary migration. Beginners sometimes believe there is a correct threshold that the model can find automatically, but the correct threshold depends on operational capacity, the cost of misses, and the quality of downstream review. A thoughtful threshold is one that matches how the organization can respond, not one that makes the model look impressive in a chart. In practical terms, thresholding is part of designing a system, not just configuring a model. A helpful way to reason about thresholds without getting lost in numbers is to think in terms of workload and value. Suppose an operations team can realistically review a certain number of anomaly candidates per day, and only a subset of those reviews will uncover meaningful issues. You want a threshold that produces a manageable queue where the top portion is enriched for truly relevant cases. That framing keeps you focused on outcomes rather than on abstract score cutoffs. It also encourages you to measure performance using precision-like thinking, meaning how many flag cases are actually worth attention, rather than only recall-like thinking, meaning how many anomalies you could theoretically catch. In security settings, a model that floods analysts with weak anomalies can be worse than no model because it teaches people to ignore alerts. Beginners also need to understand that an anomaly threshold should be revisited as data changes, because a threshold that produced 10 alerts yesterday might produce 100 alerts tomorrow after a legitimate shift in behavior. Thresholds are living choices, not set-and-forget facts. Different anomaly detection approaches produce scores for different reasons, and recognizing those reasons helps you interpret what the model is sensitive to. Distance-based methods score points as anomalous when they are far from typical points, often using nearest neighbor ideas or clustering distances. Density-based methods score points as anomalous when they fall in low-density regions, meaning few neighbors are nearby in the feature space. Reconstruction-based methods, often associated with neural networks, learn to compress and reconstruct normal patterns, and then score anomalies based on how poorly a point can be reconstructed. Each of these approaches is making a different bet about what abnormal looks like, and each one can fail in predictable ways. A distance method can be misled by scaling or by irrelevant features that distort geometry. A density method can struggle when normal behavior has multiple densities, such as some user groups being highly consistent and others being diverse. Reconstruction methods can mistakenly reconstruct anomalies well if they are common enough in training, which can hide real risk. Thoughtful use means you choose a method whose sensitivity matches the kind of unusualness you care about. An important beginner misunderstanding is assuming that anomaly detection is best when it finds rare events, as if rarity automatically equals danger. In reality, many rare events are harmless, such as an employee traveling, a one-time administrative fix, or a new service integration, and many dangerous events are not rare in isolation, such as repeated login attempts or common scripting tools. Anomaly detection is most effective when the features represent behavior in a way that makes malicious patterns stand out relative to normal operations. In cloud security, that often means capturing context, such as which account performed an action, from where, on which resources, and in what sequence. If you only use raw counts, you might flag high-volume workloads as anomalous simply because they are busy, not because they are risky. If you only use static attributes, you might miss suspicious behavior that is normal for one role, but not for another. The safe posture is to treat anomalies as prompts for explanation, not as conclusions about intent. Overclaiming is avoided when you consistently ask, unusual compared to what and why. Drift is the reality that makes anomaly detection both valuable and fragile, because the definition of normal changes over time in almost every real system. In cloud environments, drift can come from new applications, policy changes, seasonal business cycles, new team structures, and changes in attacker behavior that alter the background noise. An anomaly detector trained on last month's normal may flag this month's legitimate change as anomalous, producing a burst of alerts that are technically correct under the old baseline, but operationally unhelpful. Drift also works the other way, where a model can slowly accept new abnormal behavior as normal if it is repeatedly observed, which can hide emerging threats. Beginners often assume that drift is a rare edge case, but in practice it is the default, especially in fast-moving environments. This is why anomaly detection systems should be monitored not only for accuracy, but for score distribution changes, alert volume changes, and shifts in which features drive anomalousness. Treating drift as inevitable helps you design safer thresholds and update strategies. Understanding drift also helps you avoid a common mistake, believing that a model that once worked will keep working without attention. Because anomaly detection often lacks labels, it can be hard to notice performance decay until the operational impact becomes obvious, such as alert volume spikes or missed incidents discovered later. A disciplined approach is to treat anomaly detection as a monitored service, where you watch for changes in baseline behavior and for shifts in the score distribution that indicate the model's notion of normal is no longer aligned with reality. In cloud security, this can include watching changes in user populations, new service accounts, changes in geographic access patterns, and new pipelines that generate different event frequencies. When you observe drift, you have choices, such as adjusting thresholds, updating the model with newer data, or segmenting the baseline, so different groups have different notions of normal. Even without hands-on steps, the core idea is that anomaly detection is a moving target, and safety comes from acknowledging that movement. Overclaiming disappears when you frame the model as an evolving guide. Segmentation is one of the most practical conceptual strategies for handling drift and for improving anomaly detection quality, because it reduces the burden of defining a single normal for everyone. Instead of one global baseline, you can think in terms of baselines per user role, per service, per environment, or per workload type. This helps because what is normal for a deployment pipeline is not normal for a human user, and what is normal for a database service is not normal for a web application. By narrowing the comparison set, the model can produce more meaningful scores because it is comparing like with like. Segmentation also reduces false alarms caused by mixing populations, which is a common reason anomaly detection feels noisy. In a security context, segmentation aligns naturally with least privilege thinking because different identities and systems should have different expected behaviors. Beginners sometimes see segmentation as extra complexity, but it is often the difference between a useful anomaly signal and a useless one. Thoughtful segmentation is not about making the model fancy. It is about making normal a fair comparison. Evaluation in anomaly detection is tricky because labels are often missing, but thoughtful evaluation is still possible if you avoid pretending you have certainty you do not. You can evaluate ranking usefulness by sampling from different score ranges and reviewing what you find, which helps estimate how enriched the top alerts are for meaningful issues. You can evaluate stability by checking whether the same kinds of cases stay near the top over time or whether results are dominated by randomness and data artifacts. You can also evaluate operational metrics, such as whether alert volume is manageable, whether analysts can act on the information provided, and whether investigations are faster or more targeted. In cloud security, a useful anomaly system often improves time to triage by surfacing unusual activity with enough context to guide the first investigative steps. A common beginner mistake is to report only internal clustering or distance metrics and assume that proves the anomalies are real. The honest evaluation story is grounded in sampled review, stability, and impact on decisions, not in an illusion of ground truth. Another area where overclaiming appears is in the language people use to describe anomalies, so it helps to practice careful phrasing. Saying an event is anomalous means it is uncommon under the model's baseline, not that it is malicious. Saying an event has a high score means it is ranked as unusual, not that it has a high probability of being an attack. When you must communicate to stakeholders, it is better to describe the anomaly detector as a prioritization tool that highlights deviations from learned patterns, and to explain that the system needs human judgment or additional corroborating signals to confirm risk. This is not cautious for the sake of caution. It is accurate modeling communication that prevents automation bias, where people trust a model too much because it sounds objective. In security operations, automation bias can lead to wasted effort on noisy alerts and dangerous neglect of low-scoring but high-risk events that look normal. Using careful language is part of safe system design because it shapes how people respond. Avoiding overclaiming is a technical and human factors responsibility. Bringing these ideas together, anomaly detection is best approached as a scoring and prioritization problem under changing conditions rather than as a simple yes or no detector. Scores rank unusualness, thresholds convert ranking into workload, and drift constantly reshapes what unusual means in real environments. Distance, density, and reconstruction approaches each produce scores for different reasons, so the method you choose should match the kind of unusualness you expect and the kinds of failure modes you can tolerate. Segmentation helps because it makes normal more specific and reduces noise, especially in diverse cloud environments. Evaluation remains essential even without perfect labels, and it should focus on sampled usefulness, stability, and operational impact rather than on dramatic claims. When you avoid overclaiming, you protect stakeholders from misunderstanding, and you protect the model from being blamed for problems it was never designed to solve. This is what it means to use anomaly detection approaches thoughtfully, and it is a core skill for using data AI methods responsibly in cybersecurity contexts.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.